Okay, the N3 question assumes that we've released the pressure by releasing the valve or something. The gas expands quickly. Now, you want to think of the gas not as expanding and escaping out into the atmosphere, but rather as maybe expanding into some kind of a low-pressure air bladder that accepts the gas without changing the pressure of the system as a result. So the gas will have undergone an adiabatic expansion by the time it gets to state 3. Between state 2 and state 3, you have an adiabatic expansion. And I wonder if I got my subscripts wrong in some of the previous. No, I think I used V1 and V2. Okay. So the gas has undergone an adiabatic expansion. Now you have P3, V3, and T3. You have the work done between states, the change in internal energy, and the delta Q between the states. We want to think of each of these things separately. Again, we want to think of internal energy and work done, and then think about the delta Q rather than using some formula. Okay, so we have, what do we know about between state 2 and state 3? Well, we're releasing the gas back to atmospheric pressure. That was the original pressure of the system. So P3 equals P0. P0, of course, was 100 kilopascals. We don't know what pressure in state 3 is, but we can calculate it. Well, actually, we do know the pressure in state 3 is going to be equal to P0. Okay, what about the volume? Well, we know the gas is going to expand, so we know the volume is greater than the volume 2, but we don't necessarily know how much greater. What about the temperature? Well, if we knew the volume, since we know the pressure, we could find the temperature. Again, N isn't changing. The gas is just going into a different part of the system when we do this expansion. So we don't necessarily know T3. So we're kind of stuck until we go back to what we saw last time. Now, I didn't prove this. We can prove it if you want to, but somebody's going to have to ask me because it's in your book. It uses differentials and such things. It's not that difficult of a proof, but right now you want to just grab onto the idea that PV to the gamma is constant. Okay? Gamma being the ratio of the specific heated constant pressure, which is 7/2 R, to constant volume, which is 5/2 R for a diatomic gas, 1.4. Saw that last time, so this is nothing new. Well, that means that P3V3 to the 1.4 equals P2V2 to the 1.4. And as far as that goes, it equals P0V0 to the 1.4. We could use pressure and volume at any stage to and set it equal to P3V3 to the 1.4. But we'll use P2 and V2. And if we solve this for V3, the solution is very simple. We divide both sides by P3, then we take the reciprocal 1.4 power of both sides. That gives us the reciprocal 1.4 power of P2 over P3, and the reciprocal 1.4 power of V2, which is just the reciprocal 1.4 power of V2 to the 1.4. Well, that's just V2. Calculating this and the 0.56 liters, I came out with an estimate of 0.6 liters. They said that's probably good to within a hundredth of a liter. Turns out, incidentally, not bragging or anything, just one of those neat coincidences where I'm more accurate than I deserve to be. It actually came out 0.599 liters. So my intuition was it was between 0.6 and 6.1, closer to 6. It was actually a little less than 6, so I didn't do all that well. Just lucked out, and it turned out that rounded out to what I estimated. Okay, well, no big deal there. So we didn't finish this. I'm going to finish this in another clip, but let's review. Let's finish up what we did in class, so nobody has to watch this again if they already understood it. And then I'll do the rest in a separate and relatively brief video. Okay, so what do we do now? Once we know V3, we easily calculate T3. Now we go through the usual rigmarole with the gas law, PV over T equals constant, and rearrange it so with P with state 2, state 3. This should make sense. T3 should be the ratio of the two pressures, this pressure being less than this, times the ratio of the two volumes, this volume being greater than this volume, multiplied by T2. Now, remember the volume ratio is the reciprocal 1.4 power of the pressure ratio. The reciprocal 1.4 power being less than 1 is going to give you a ratio less than the 110 over 100 ratio of the pressures. And of course that ratio is P2 over P1, not P2 over P3, not P3 over P2. If you think about how those ratios change, you'll see that the magnitude of the factor here and the magnitude of the factor here are different. So that T2 is, or T3 is going to certainly be less than T2. Okay, you can think that through with the numbers and the relative sizes of the numbers, the ratios. Okay, well, having done that, we need to get the work from state 2 to state 3. Now, having found the temperature in state 3, we're going to be able to find the internal energy. And then, therefore, the change in internal energy. We've got to find the work, and to do that, we've got to integrate the pressure with respect to volume. And we observe, as we saw last time, that the pressure times volume to the gamma being constant, or this equation here, which I'm not going to read to you, if P and V are the pressures at any stage, PV equals P2V2, PV to the 1.4 equals P2V2 to the 1.4 at any point during the expansion, so that P equals P2V2 to the 1.4 power divided by V. Now, we didn't have time at the end of class to do all the details of the calculation, so I'm going to follow up with those in a separate video.